Hello guys, how are you doing? I'm Mohammad Sadri and this is lesson 10 part 2 using AXI DMA in scatter gather mode. And what I'm going to do in this video is that I'm going to use the hardware that we created in the previous video, and I'm going to practically test the functionality of my AXI DMA module in scatter gather mode on the Z board. For that, I will create a set of TCL scripts, and then using XMD I will run those TCL scripts, and then I will see if the DMA engine is working, is transferring data or not. Also, I have added some probes, ILA probes, to my hardware, and I also watch those ILA probes to see if the signals they look reasonable or not. These videos I am creating as a hobby, and I'm not responsible for the correctness of what I am saying here. I practically test the design on the board, but these videos, they are not official, so I'm creating them for myself. Before I continue, I will show you the document that we will refer to continuously during this video. The document, which is the main reference for using AXI DMA module, is titled ZYNQ AXI DMA Product Guide. Its code is PG021, so when you search in the ZYNQ's website for the document, you can search for this code and you can download the latest version of the document. So here is the document itself, the one that I'm going to use, and this is the guide. So here I have in fact complete specification of the AXI DMA and its operation, how does it operate in either register or scatter gather mode, and the specific sections that we will look at is the register space that we need to know about. Then we also look at a scatter gather descriptor, and so basically these two sections we will really focus on and we will use them. And then the multi-channel DMA support I put for later videos. So for now what we want to test is the scatter gather functionality. So for now I go in fact to page 13, which is the beginning page for description of the registers of this module. So here, register space, here are the registers of the AXI DMA, and these registers are those which are accessible to the CPU through this AXI slave light memory mapped interface. So I come back to my presentation and then I go to the next slide. For this video I have created 4 TCL scripts. I run those TCL scripts one after another on the Z board. This is the first TCL script. This is the first test that we want to do. We set our AXI DMA engine in scatter gather mode. Then we define 2 descriptors. One descriptor for the direction of in fact a stream to memory mapped, in fact to receive the data and to put it on the DRAM memory of the PS, and another descriptor for the reverse direction from the DRAM to the output or outgoing AXI stream. So we define 2 descriptors. Each descriptor is responsible for making the DMA to perform data transfer in one of these directions. As I told you, in the AXI stream logic that I create, everything appears as packets. So I put a series of data one after another and I create a packet out of them. So it's not the case that my AXI stream logic that I have here produces in fact pieces of data one after another without indicating the boundary of the packets. So this packet sync is very important. So the logic that I have here, it also produces the T-last to indicate that, for example, this is the end of the packet, and then the other next chunk is the beginning of the next packet. So this packet boundary, the packet size, is actually very important. The packet size has a in fact direct relationship to the descriptor that you define here. So using the CPU, as I showed you in the previous video, we are creating these two descriptors. And for now, for the first test, each of these descriptors that I'm creating here is responsible for transferring one packet of any size of data to the AXI DMA engine or from the memory to outside world. So I have two descriptors. Each descriptor transfers one packet of data. So let's look at what we are going to do in a slightly more detailed level. So what's practically going to happen is the following. I have two descriptors. In each descriptor you have a pointer to the next descriptor. So since I have total two descriptors and each descriptor is for one of these directions, I have one descriptor per each direction. So practically the descriptor is pointing to itself. This pointer and this pointer. And then when I want to start the DMA transfer, I should program the DMA engine with a head and tail pointer to these descriptors. Since in this test I have only one descriptor and I am going to transfer only one packet of data, the head and the tail pointer registers are both pointing to the same descriptor. So for the mm to s direction, the mm to s head pointer and the mm to s tail pointer, they are actually the same value, and this value is the starting address of this descriptor in the block memory. And then for the s2mm direction, for the s2mm head pointer and s2mm tail pointer, again for both of these pointers, they are pointing to the same descriptor, and the value that I write here is equal, and this value is equal to the starting address of this descriptor in the block memory. So as you remember from the previous video, we have this block memory here. It's shared between the CPU and the DMA engine, and it's responsible for keeping the descriptors for us. So I'm copying, in fact, these descriptors using the CPU to this block memory, and then using the CPU I'm setting these head and tail pointers so that as I set the tail pointer, the DMA engine begins the data transfer on that specific data direction, and then it will begin first processing the descriptor which is indicated by the head pointer, and then it looks to where this descriptor points out. It goes to the next descriptor until it reaches the tail pointer, and when it reaches the tail pointer, if the cyclic bit is not active, it stops. Now for our case, since head and tail pointer, they are both pointing out to the same descriptor, what's happening is that the DMA engine will only transfer one descriptor, and since one descriptor here is responsible for transferring one packet of data, the DMA engine will transfer one packet of data in every direction. Okay, let's see how I have realized this as the TCL script. So here comes the TCL script that I have created for test number 1. I uncomment this part. So if I look overall at this TCL script, I will see a set of memory read and writes. And when later I want to write the program which is going to be executed on the ARM host, that program is basically performing the same set of read and writes to initiate the DMA engine in a scatter-gather mode. So overall, what the script is doing is that it first programs and initializes the FPGA, then it defines the transfer size. So as I told you, we don't have any limitation on the size of the packet that we want to transfer. In this test, I'm transferring only one packet, but this packet can be any size. So the transfer size parameter here can be any number that you want. And then I'm initializing and resetting the DMA engine, and then I'm writing the descriptors to the block memory, and then I'm initializing the DRAM memory, in fact locations in the DRAM memory to which the DMA engine is going to write and from which the DMA engine is going to read. And then I start the DMA engine on the S2MM direction, and then I start the DMA engine on the MM2S direction, and then I start my own sample generator module about which I talked in the previous video. And then finally I wait 1 second, and then I show you in fact the results. If the data transfer is done or is not done, what's the status of the DMA engine, and what's the data that our sample generator has received, if our sample generator has received any data or not, and if the data transfer has been successful or not. So as I told you previously in the previous video, the AXI MM2S port of the DMA is connected to our AXI port of the sample generator. It means that the data that our DMA engine reads in fact from the DRAM memory through the AXI MM2S port from the DRAM memory, the data will be forwarded over this AXI stream port to our sample generator. And as I described to you in the previous video, my sample generator counts how much total data it has received over this AXI stream interface. It also counts number of packets that it has received over this AXI stream interface, and it also shows the in fact the heading and the tailing chunk of data for the last packet that it has received. So when I run this TCL script, then when the transfer is done, I can look at these registers in my AXI sample generator and see the statistics of the data that it has received. Also I have the ILA probe and I can look at them. So before I go into detail of how in fact I'm programming the descriptors, I want to very briefly tell you what are the next tests that I'm going to do. So after I did the test 1 completely, I go to the test 2. In the test 2, in each direction I use 2 descriptors, and each descriptor is responsible for transferring 1 packet of data. So total I will read 2 packets and I will write 2 packets on the output stream. In test 3, I have total 4 descriptors in each direction, and each of 2 descriptors are responsible for transferring 1 packet. So this 1 and 2 are responsible for transferring this packet, and then 3 and 4 are responsible for transferring 2 packets, the second packet. So in total I'm transferring 2 packets in each direction. I have 4 descriptors. Each 2 descriptor is responsible for transferring in fact 1 packet. So the transfer task here I have divided between 2 descriptors. The first descriptor in fact tells the DMA engine or instructs the DMA engine to transfer the first chunks of data of the first packet, and then the second descriptor instructs the DMA engine to transfer the second chunks of data of the first packet again. and then this guy goes for the first part of the second packet, second part of the second packet. And the same thing is holds true for, in fact, S2MM direction. And then finally in test 4, what I'm going to do, test 4, sorry, this is test 4. What I'm going to do, I'm going to enable the cyclic mode in the DMA engine so that the transfer will continue forever. So basically I keep what I have from test 3, and then I enable the cyclic mode, and as I will show you, in fact, in a cyclic manner, the DMA engine will process these descriptors, and in parallel for both of the directions will perform the instructed transfer tasks. Okay, so I come back to, in fact, test 1, and then I come back to the TCL script that I have here, and actually what you see here is I'm using the CPU, I'm initializing that block memory, this block memory which is responsible for holding the descriptors. So I'm programming that block memory, and in fact this is a one descriptor for transferring data in the direction of MM to S, and this is the next descriptor for transferring data in the direction of S to MM. And actually here is the content of the descriptors. I can look at my AXI DMA document to tell you the meaning of each field. So if I scroll down here through the document, I will reach a table which shows me, in fact, the fields of each of the descriptors. So here you have the table, and the definitions that I have here are exactly based on this table. So the first two fields are indicator of the next descriptor. So the first two fields are the indicator of the next descriptor. The second one is the higher 32-bit address of the next descriptor, and the lower one is the lower 32-bit address of the next descriptor. And as you are seeing, the next descriptor as the pointer to the next descriptor, this is currently pointing to itself. So the address for the next descriptor I have written, it is 0x40000, and it's exactly the address of this location in the memory. So it's pointing to itself currently. It's this pointer that I showed you. And the same thing holds true for the S2MM direction. For the S2MM direction, I'm using the second part of the block memory to keep the descriptors that I need for the S2MM direction. So the first part of the block memory I use for keeping the descriptors that I'm going to consume for the MM to S direction. The second part of the block memory I am going to use for descriptors that I need for S2MM direction. All of the addresses that you have in the AXI DMA, they are 64-bit addresses. Okay, and so if you are using the AXI DMA in a 32-bit system, always the second one is 0. Okay, now we continue. In fact, I bring the document. Here we have buffer address, and again the upper 32 bits of the buffer address. So if I look at the script that I have written for the MM to S direction, I am using this physical address in the DRAM memory, from which the DMA is going to read the data, and then it will put the data on the AXI stream output. And for the S2MM direction, I'm going to, in fact, read the data from the incoming AXI stream, and I will put the data at this physical address in the DRAM memory. So this is the buffer address for S2MM direction, buffer address for MM to S direction. Next field. Next field is these two are reserved, and then we come to control. And actually, what does the control do? The control will provide us three very important parameters. So if I scroll down to the description of control field, we have it here. So the value that I'm writing here to this address, control, and here to this address, control, for the S2MM direction. This value actually contains three important pieces of information for the DMA engine. First is the transfer size. We are telling the DMA engine how much data we want the DMA engine from this address to transfer, or how much data the DMA engine should read and write to this address and to the subsequent addresses. So this is the transfer size. And then it comes a very important, in fact two very important flags. That is the end of frame flag and a start of frame flag. And these two flags, they are indicating to the DMA engine if this descriptor is responsible for transferring the initial chunk of a packet or the ending chunk of a packet, or none, in fact the middle chunk of the packet. So when a descriptor that I have written to the block memory is responsible for, in fact, transferring the initial part of a packet, in fact the heading chunk and some data after the header, this flag is set. This is 1, this is 0. If this descriptor is responsible for transferring the ending chunk of a packet, this one is set, this one is 0. If this descriptor is responsible for transferring one complete packet, so this descriptor is responsible for both transferring the start part of the packet and the ending part of the packet, both of these guys are set. They are both 1. And if this descriptor is kind of descriptor which is in the middle, is responsible for transferring the middle part of the packet, both of these guys are 0. And what's our case? As I told you in the in fact presentation, each of these descriptors is responsible for transferring one complete packet. So one descriptor transfers both the start part of the packet and the ending part of the packet, or the start part of the frame or ending part of the frame. So I have here put both of these bits into 1. Okay, if I scroll up, we have the control, we have the status. Actually the status is something that is extremely important. The AXI DMA engine will write to it as it processes this descriptor. So later we can look at this, or the CPU can look at this status field and check if the DMA engine has transferred the data correctly or not, or what's the status of the transfer, what's the status of, in fact, this descriptor being processed. And then we have user application fields, which for now we don't use, so I have keep them all equal to 0. Okay, the rest of the TCL script, this initialization of those read and write addresses in the DRAM memory. One important note is that if you are running these TCL scripts, if you have downloaded these TCL scripts out of my Dropbox folder and you're running these TCL scripts, the point is the transfer size, as I told you, can be any number, you know, so the limitation is only this this size that you see here, 23 bits. So 23 bits means 8 megabytes. You can transfer, you can tell the DMA engine in each descriptor to transfer for you up to 8 megabytes of data. That's the only limitation. Okay, but here, if you decided to put a big number here, please note that these guys, they will take a very long time to be executed. Okay, so this is not the most efficient manner with which you can really initialize the memory through the XMD. Okay, so if you use the big number here, either change this part, use another method to initialize the memory copy, or comment out this part. So this will take time. Okay, so now we come to a very important point, and that's where we want to, in fact, start the DMA engine in each of the directions. Okay, the first thing that we do, as I told you in the presentation, we should write the value, the address for head pointer. The head pointer should be written, then the tail pointer should be written, and as you write the tail pointer, if the DMA engine is active, it will begin the transfer operation. So this is what you see here. For the S2MM direction, I'm writing to the DMA engine the head pointer, the address for the head pointer. Then I'm starting the DMA engine, and up to this point nothing will happen. As I write the tail pointer to the DMA engine, the actual transfer will begin. The same thing is true here. We write the head pointer, we start the DMA engine, nothing will happen. As I write the tail, the transfer will begin. So for the S2MM direction, when you write the tail pointer, in fact, what will happen, the DMA engine will begin looking at its incoming AXI stream port to see if any data is present, to transfer that data to the DRAM memory. And in my script, I have enabled my sample generator here. Okay, so practically what will happen is that when you write the tail pointer here, since my sample generator is not still active, nothing will happen in the S2MM direction until I enable my sample generator. But for MM2S direction, as you write this tail pointer, the DMA engine will begin immediately reading the DRAM memory and putting the content of the DRAM memory on its outgoing AXI stream port. So when I do or I run this script on my Z board, I expect to see this one gets finished first, and then this one gets finished later. Okay, so as the final description I want to give you in this in fact, for this TCL script are these addresses that you see here. What are these addresses? These are actually the addresses which are accessible through this AXI memory map light interface. So if I look at the address editor from the viewpoint of in fact ARM host, the AXI DMA engine is located at address 40400000. Okay, so if I now look at my in fact TCL script, I see that these are registers of the DMA engine which is located at this address, and these registers, the description for them, the complete description for them is present in this table that I showed you in the beginning, the table which shows the register map of the DMA engine. Okay, and the second description or second point that I want to tell you here is that this address that you're writing here is the address of the descriptor from the viewpoint of the DMA engine. Okay, so this address is the address of the descriptor from the viewpoint of the CPU. This is the address using which the CPU will access this block memory. This is the address through which the CPU sees this block memory, and this address is not necessarily similar to the address through which the DMA engine sees the block memory. So for our case, these two are the same. So the automated address generation system of Vivado has put this block memory in the same address location, on the same physical address value for both of the AXI memory map master port of the DMA and for the GP0. Okay, but this is not necessarily true. So it can happen that these two are different. In fact, the address through which the CPU sees the descriptor is not necessarily exactly similar to the address through which the DMA sees the descriptor. Okay, that's it for now, and now I come here and I just clean up my XMD my console, and we can perform the first test. So what I do, I turn on my Z board, and now the Z board is on, so I say XMD source test 01.tcl, and all of those steps that I told you will be done. The FPGA will get programmed, the PS will get initialized, the DMA engine will get to start the operation, and here are the results. So actually this is the amount of data that my sample generator has received from the DMA engine. So is 1F, and if I look at my calculator, 1F, it has received 31 bytes of data from the DMA engine. And if I come back to my, in fact, TCL script, the amount of transfer that I have defined is 31 bytes. So I had packet of 31 bytes. I told the DMA engine transfer for me 31 bytes. And as you see, the DMA engine has performed the transfer. This is the heading of the packet that I have received, this is the ending of the packet that I have received, and actually we have transferred one packet. Now if I look at my descriptor for the S2MM direction, I see that I have instructed the DMA engine to put the data of the AXI stream port at this address. So now if I come here and read the content of this address in the memory, I can see that the DMA engine has transferred 1, 2, 3, 4, 5, 6, 7 multiplied by 4, 28, 29, 30, 31 byte of data for me. Okay, so the important message that I want to give you here is that the DMA engine should be able to transfer for you any amount of data that you want. It should not crash, it should not stop. It's not needed to transfer necessarily multiple of 4 bytes. You should be able to transfer any number that you want if you configure this thing correctly. And if your AXI stream interfaces, they are operating correctly, you should be able to transfer any data that any amount of data that you want. There should be, in fact, no limitation of this type. Okay, now I want to repeat this test, and this time I want to look at the waveforms. So I turn off my Z board, I turn it on again, and then I enable the probes, and then I will repeat the test to see the signals. Okay, I repowered the Z board, and now in my TCL script that I have here, I comment out these lines. Why I comment out these lines? Because I want to in fact put them manually on the XMT console. At this point here I should enable my ILA probes, okay, and obviously not before that, because before that the PL does not have any clock. So what I do, I come here, XMD, and then these commands one by one, connect ARM hardware, and then program the fabric, and then initialize the PS, and then the famous PS underline 7 init, and then the famous PS7 underline post config. So now is the point that I can enable my ILA. The PL has a complete clock, the ILA has a clock, so I can come here to my Vivado design environment, and then I can open my flow navigator, and then I can come down and I can say open hardware manager, and then open target, and then auto connect, and then I have the interface with the list of signals that I indicated at video number 1. As I showed you, I indicated a set of signals to be connected to an ILA core. Okay, and now I have put my ILA machine into basic mode. So what I want the ILA machine to capture, I want the ILA machine to capture the values of these waveforms only when either the T valid on the slave interface is active, or the T valid on the master interface is active. So I don't want the ILA to capture every clock cycle data for me. I want the ILA to capture data only when actually it's in this clock cycle, in that clock cycle, a data transfer may occur. Okay, because the reason for that is that the length of the buffer that I have for the ILA is limited. I have total number of 1024 samples, and with this total number of samples I want to see what happens on both of the channels, on both of the incoming AXI stream channel and outgoing AXI stream channel. And so I have instructed the ILA to capture the data only when actually there is the probability that a data transfer will happen. Okay, so I have this setup here, it's in basic mode, and this one is empty. Actually I don't have any trigger. I have here this one, and then I put this guy into, in fact, post trigger mode, and then now I can run my TCL script. So source test 01.tcl, the outcome is exactly the same as before, and now what I have here, in fact, I have a representation of what has happened actually on each of these two AXI stream interfaces. So let's have a look. This is actually very simple. Okay, I want to make it slightly bigger. Okay, so what I have here are the set of signals on the AXI slave port of my sample generator, and these are the set of signals on AXI master port of the sample generator. These are the signals which are coming from the DMA engine. These are the signals that I am sending to the DMA engine. Okay, and what we see here, we see one complete packet is transferred. So we have the TLAS, we have the T valid. So the DMA engine has sent us one complete packet of this data, which is actually the data with which I initialized the DRAM memory. And on the other side, from the sample generator to the DMA engine, again we see the transfer of one complete packet. Here I'm not showing the T data because, as I told you in the previous video, the ILA would get very big if I wanted to use the T data. So we have the T last here, and then we have the T keep. Obviously the T keep for the last chunk of data is 3, for the rest of the chunk of data it's 7. And as I told you, I'm not showing the LSB bit, so the bit 0 I'm not showing here because it's always 1. And then we have the interrupts. So when the transfer on the MM2S direction finishes, this interrupts get generated, gets activated to the CPU, and when the transfer on S2MM direction finishes, this interrupt gets activated. And the delay here between the T last and the interrupt, as of what I think, is that actually the interrupt will happen when the data is written to the DRAM memory. So you have received the data here, and then as the DMA engine receives the data here, there's a latency between actually receiving the data and making sure that the data is completely written to the DRAM memory. And this latency is the latency with which we see the S2MM interrupt out happening. Okay, so this is now kind of completely described. We can go to the next test. Okay, here is a more descriptive sketch of what we are going in test 2. We have 2 descriptors in every direction. The first descriptor is pointing to the next descriptor, and then the next descriptor is obviously pointing to the first descriptor, but since the cyclic bit is not active, this one does not have really any effect. And then for the head and tail pointer, the head pointer for each of the MM to S direction, S to MM direction is actually pointing to the first descriptor, and the tail pointer of each of MM to S and S to MM is pointing to the second descriptor. So here I have test 2, and what I do, I run this test and I see if it's working fine or not. So here xmd source test2.tcl. Yeah, so I have probably a problem with connecting to my Z board through xmd, probably because this guy was open. And okay, the problem looks more serious than what I was expecting. Just one moment, I come back. Okay, I hope this time it works. So xmd source test underline 02.tcl. Okay, so this is the output of the second test. We have received 2 packets, total of 3E bytes. So 3E is equal to 62 231, and then if I look at this location in the memory, it's where the S2MM data is written. So I have, in fact, the first piece of S2MM data is written here, and then the second piece of S2MM data as of the descriptor that I have defined, and then you can check out for yourself later, is written here. So the first piece, the first packet, I have instructed the DMA engine to write the first packet here, the first 31 byte of data, and then in the second descriptor I have instructed the DMA engine to write the second packet here. And as you see, for both of them 31 bytes of data is transferred and the system is operating correctly. Now I go ahead with the next test, test number 3, and in test number 3 we have 4 descriptors in every direction. And the interesting thing about this test 3 is that as I told you, two descriptors are responsible for transferring one packet. So here I have test 3. The interesting point here is that in the definition of the descriptors, the first descriptor is only responsible for transferring the, in fact, start of frame, the initial part of the frame, and then the second descriptor is responsible for transferring, in fact, the ending part of the frame, the second part of the frame. And then I have defined transfer size 1, transfer size 2, and then these transfer size 1, transfer size 2, the first one is 32 bytes, the second one is 28 bytes, total packet size is 60 bytes. So I expect when I run the test to see two packets, each 60 bytes is transferred, total 120 bytes should be transferred. So I come here and then I do the test. So xmd source test 03.tcl. Okay, so here is the outcome. The sample generator has received two packets, total amount of 78 hex bytes. So this one, if I look, 78 is equal to 120 bytes. And this is what we described in fact our TCL script. We have each packet is 60 bytes, two packets, total 120 bytes, and then on the other direction I can check if 60 bytes is transferred. So 60 bytes, and then also the other address, another 60 bytes. Okay, so this is also working fine, and now we go to our final test. And in the final test that we have 4 descriptors in each direction, and the descriptors are pointing to one after one the other. So 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4. 1 is responsible for transferring the heading, the start of frame. 2 is responsible for transferring the end of frame, and again start of frame, end of frame. And now the cyclic mode for the DMA engine, this time I have made it enabled, and for the head pointers are actually pointing to descriptor number 1 on each direction. But the tail pointer, when you want to do cyclic transfer, practically the tail pointer is not pointing to anywhere. So as you see, the tail pointer is pointing to a descriptor that does not exist, and descriptor number 4 is pointing to descriptor number 1. What will happen is that the DMA will begin in fact processing the descriptors 1, 2, 3, 4, and since this is not equal to the tail pointer, it looks for the next descriptor. It sees the next descriptor is 1, so it jumps to process descriptor 1 again. Okay, so if I put the tail pointer here, if I put the tail pointer on descriptor 4, regardless of descriptor 4 pointing to in fact 1 or not, regardless of this fact, what will happen is that the DMA engine, as it reaches the descriptor number 4, and as it sees that this address is equal to the address of the tail pointer, it stops the processing. Okay, so for cyclic mode, whenever you want to transfer data forever or for a while until your CPU in fact stops the DMA engine manually, if you want to do that, the tail pointers should not point to anywhere. Okay, so here I have number 4. The configurations are the same as before, only in writing the descriptors. The final descriptor number 4 is pointing to the first descriptor, and then at the end what I'm doing, I'm enabling the cyclic bit. So when I'm starting the S2MM direction and MM2S direction, when I'm starting the DMA engine in each of these directions, I'm enabling the cyclic bit. Okay, so I do this test here. XMD source test for TCL. Okay, so now I see this is the amount of data that my sample generator has received so far. So up to this point that a read happens, this is the amount of data that the sample generator has received. Now if I continue reading from that location in the memory, what I see is that this number is incrementing continuously. Why? Because the DMA engine is running and it is sending data to my sample generator. And on the other hand, if I read the next one, the next register is the total number of packets that I'm receiving. As you see, it is incrementing because the DMA engine is running and it's reading the DRAM memory and is sending data to my sample generator. And on the other hand, if I check the DRAM location at which the DMA engine is writing the data, as you see, is changing constantly. Why? Because the DMA engine in the S2MM direction is receiving data from my sample generator and is writing this data to the DRAM memory continuously. So the DMA engine is active in both directions. In S2MM, MM2S, it is active and is working continuously. And if I want to in fact stop that, what I can do, in fact the first bit of the control register of the DMA engine I can set to 0, and by doing that the DMA engine will stop in the direction that I want. So these are the 4 tests that we did, and now we are sure our hardware is fine, our hardware is working perfectly. So what we can do, we can go to the next step in which we write a software which is being executed on the ARM host, and then it performs the same type of programming the DMA and defining the descriptors and initiating data transfers. Okay, that is the end of video lesson 10 part 2, and then we will go toward the next video part 3 in which I create the software. Okay, thanks for watching. Bye.